All right, so I think this topic is probably the most useful topic in all of algebra. And we're going to spend a little while on it. So today's just an introduction to something called systems of equations. And we're going to look this year at 2x2 systems. So a 2x2 system of equations, also known as simultaneous equations, although I think that's kind of an outdated term. It's two equations, two variables, and we can solve for both variables. Okay. So here's kind of an example of where something like this might be applied. Right? This is sort of a classic example. Let's say you are a Navy commander, right? And you see this this enemy submarine coming towards your base. Right? Well, if you have enough data about that submarine, you could figure out how fast it's going and where it will be at a certain time. In other words, you could sort of plot a trajectory, right, for that submarine. We might say, this is the path of that submarine. I can sort of, that made no mark on the board. Marker is apparently not going to work. I can sort of, make a graph of where the submarine will be at a given time. Well, if it's an enemy submarine, we want to launch like a torpedo at it or something, right? And I know enough about my torpedoes that I can figure out the trajectory of my torpedo as well. So here's here's maybe a possible trajectory of my torpedo. But I'm going to base the trajectory of my torpedo off of what I know about the submarine so that the torpedo hits the submarine at a certain point. Okay? And there's millions of other examples of this sort of thing, where we know the path of one object and we can adjust the path of another object to make them hit or cross or meet at a certain point. And that's kind of the idea with systems of equations. And it even goes beyond that, beyond sort of a physical path, right? We might be able to come up with an algebraic linear equation that represents something, an algebraic linear equation that represents something else, and combine them. So another classic example is something like, we know the price of tickets for children and adults to go into a carnival, right? And then we maybe know the total number of people that we had at this carnival, and by sort of combining those two pieces of information, we can create a system of equations that tells us exactly how many adults and exactly how many children were at the carnival. So it's this idea of combining different pieces of information to solve for two different variables. Okay, and we will eventually look at some specific word problems that use systems of equations. You could actually use these to solve word problems we've already looked at. You could use them to solve age word problems, for example, if you wanted to. But for now, we're just going to look at the equation part of it. So I've written two equations on the board. Y equals 3x minus 6 and y equals negative 5x plus 2. Okay. If we want to know the solution to those two equations, in this case, the simplest thing to do is just to graph both of them. So y equals 3x minus 6, I would graph that 5, 6, right, using my kind of slope-intercept method, go up 3 over 1, up 3 over 1, up 3 over 1, up 3 over 1, and one last time. And then I have the first equation, a perfectly straight line. And I have my second equation here, y equals negative 5x plus 2, so I go up here, plus 2, down 1, 2, 3, 4, 5 over 1, hey, down 1, 2, 3, 4, 5 over 1, and Oh man, that one was even worse than the first. As I noticed when I was graphing these met right at this point, which is 1, negative 3. So this would be the solution to both of these equations together. It's the point where the lines meet on a graph. And this is one of the first examples of something that we can understand or we can look at algebraically, and we can understand or look at it on a graph. And it's two different ways of looking at the same thing. Okay? So if I have two equations, both equations have two variables, I really have two lines. This is a line and this is a line. And so in this case, I'm looking for the point where these two lines cross on a graph. Okay? Now, let's just do one more example. Keeping my graph here. Let's say I had something like this. 2x minus 3y equals 6.
Then would you use a t-chart?
Okay, so that's called standard form, right? But it's still an equation, it's still a line, it has two variables, right? So I'm going to be able to graph that. Let's just graph it, just so we review. How do I graph this? If x is 0, y is, negative 2. Right, because negative 3 times negative 2would be 6. Y is 0, x is 3. And then I plot those 2 points, 0, negative 2, and 1, 2, 3, 0. Okay. And then let's say I had another one. I don't know, maybe it's something like 4x plus 3y equals 12. How would I graph this one? Okay, if x is 0, y is 4. If y is 0, x is 3. Good. Okay, so 0, 1, 2, 3, 4. 0, 1, 2, 3. Hey. Where do they meet? 3, 0. Okay. So I'm just graphing the two lines and finding the place where they meet. That's all we're going to do for today with systems of equations. Is we're going to think of them as lines and try to find the point where those two lines